rapid speed of digitization. We're talking, as we'll all be aware, that we went from the old brick phones of, say, the 80s, where they had their own battery powered carry cases, to now very smartphones in our pockets. And with that, they come with additional functionalities, as we'll all be aware, so accelerometers and GPS. So there's additional functionality that kind of is attached to iPhone and Android phones these days, which just allows us to do a lot more. They carry a lot more information, so we all have endless photos on our phones. And additionally as well, the hardware is changing as well. So if we were thinking of terms of the latest types of phones from, say, Apple or now Google, you tend to see that actually the chip design itself is altered to take into account the higher levels of numerical processing. So TPUs are an example of tensor processing units, and they're becoming increasingly more common. Occasionally you hear them referred to as like neural engines. So, and then finally we have the cloud. So we're all aware of the cloud. COVID has clearly accelerated its adoption in local government. I dare say everyone on this call had some idea of the rush to get home working done, and now that we have everything in further abstraction in cloud, we can connect things together more easily, particularly if you're on a single supplier like Microsoft, where everything can interconnect to every other project much more easily. And then finally, it's about the data itself as well. So in relation to what's called the 5 Vs, and originally it used to be 3 Vs, but now it's now 5. You can see them already sort of listed: the volume, velocity, variety, veracity, and value. And if we just to sort of touch on veracity, for instance, and the correctness of data, we also talk about things around statistical bias measurement, software bugs, noise, outlier, duplication of data as well. So the kind of what is the data about, how are we measuring it, and what's the kind of underlying issues and things that's potentially right or wrong with it as well. So it's an additional factor to take into account. Depending on the type of council you are, we actually have the Fire and Rescue Service as part of Warwickshire County Council. So again, in the future, if we were thinking of growth of data, you would have vehicles or appliances, so fire appliances fitted with telemetry, so we know where they are all the time, and that leads to more volume, greater variety as well. And again, actually, it adds to the correctness of the data as well, because it's highly accurate. But also as well, so from a district level, you may have a range of vehicles or something like that. So you can see how measurements are increasing, and that's what you tend to talk about when you talk about the growth of data. So that's how we've got to the position we are. Okay. Oh. So in general, I think we probably know data more as a CSV, Excel, SQL, for those that maybe don't know SQL, relational databases. So that's probably the most common one that we're most aware of. Time series is more common these days. I know we would say population data is a time series, but if you think of, say, your emails coming and going out of your organization, they all go with timestamps that can all be measured as well, in terms of themes and topics and underlying you know, the underlying sort of how frequent that data comes and goes. Text is now becoming a more well-identified source of data as well. So if we think of, whereas before we would tend to think of, say, a letter as information, we now tend to think of it as actually this can be broken down into its underlying words. We can count the words, we can look for structure in sort of distance between those words and how they relate to one another. So text is probably the largest one and probably most relevant to a local organisation these days. But again, depending on video and audio, these are now potentially quite large in their own right. So if we thought of telephone calls that you're getting into your organisation, you know, how do you deal with that call? I think we've all dealt with a bank where they ask you to say what your complaint is about or what the purpose of the call is, and you have to say. So that audio data can also now be interpreted and be made use of, so transcriptions and things like that. So and for video, you may find video data as particularly if you're a county council, you have video data available via scanner in highways, so where the vehicles go around and check the highways. So video data is a lot more common as well, particularly if you have vehicles that are recording where they're going. So there's a semi-structured as well, and this is probably, if you're from a more programming background, you'd know semi-structured, or semi-structured may be more common as an analyst, but now so it's called semi-structured. So actually, whilst it has some underlying data, some underlying structure to the data, actually a lot of it is still unstructured. So for instance, you can have a key value pairing, which is, you know, let's say it's a record about a person. You may say that there's a key value of case notes, but the value, it could be all the underlying text, for instance. So it can be structured, but not very structured. Okay, so the original, this is probably like the most overused Venn diagram of data science, really, which is you tend to see these overlaps, and they tend to see it as actually data science is the sort of central merging of expertise, maths and statistics, and also coding ability. In reality, it's a bit out of date. Really, for someone to have all these skills is very unlikely. They now talk about unicorns and things like that, and actually probably data science is more of a team sport these days, and so you'd have some people that are potentially very good at coding, some will have stronger maths and statistics background, but others will maybe come with two of these things, so they have expertise as well, or you may be an analyst that has both maths and statistics. You can code, but actually you're not a subject matter in, say, childcare or social services. Social care is the correct term, sorry. Okay, and just to sort of go back to the Venn diagram as well. Actually, when we talk about what it bridges the three, we're really sort of, you know, a lot of people will argue it's just really statistics, but it's not really, because you're tending to consider other aspects as well. So it's not just about the it's not just, you know, deriving a statistic, it's also the transformation of that data. In some cases it's creating potentially new variables as well from the data, or it can just be a case of reducing it in a statistical way. So it tends to go more broadly beyond statistics. And if we were thinking of in terms of COVID, certainly the mathematical applications are quite clear, particularly if people used or were aware of the charts where they show the sort of smoothing of cases going up and down, and particularly at the beginning, those sort of models around very smooth lines, which is the kind of SEER model. So susceptible, exposed, infected, and then recovered or removed. So you tend to see that. And again, further in the data science arena, if we were thinking of how people are connected to one another, so if we were thinking of social care, that tends to lend itself to graph theory. So how does the network connect to one another, and the sort of centrality of those connections as well. So, and then finally, linear algebra, which we will sort of touch on later as well. So it can broadly apply across several, but finally computer science is actually the one that it also covers in the sense of actually when you're doing data science these days, you tend to use Jupyter Lab. You may use R. We use Python, and some people use R, so it's a bit of a mixture. And ultimately, you know, some of the presentation of the data to others is through, you know, through the programs that you'll probably have to build yourself. Okay, so here's a couple of, is this a couple of examples? It's not a couple of examples, it's a single example. So if anyone was around during the, or if anyone's from a digital background, I should say, there's a web and accessible law of 2018. It's called the, I'm just checking my notes, the Public Sector Bodies, Websites and Mobile Applications Accessibility Regulations of 2018. So this is something where, as a public sector organisation, you have to be aware of how accessible your website is and how accessible your documents are and things like this. So this would be the example of, well, it would be quite difficult to assess thousands of pages without using the ability to program. So you could look at building a web tool that would scrape your own website, work out how to dissect all the text, run it through particular kind of natural language processes, and then actually score the pages themselves on, you know, based on the word count, sentence length. Is the page accessible? There are tests around this. Some are more well recognized than others, but there'd be things like smog tests and things like that, so which are used for say medical instructions for tablets and things. So really this would be an example of how you can bring together both the computer science side, the expertise around digitization, and obviously the law, and work out how to effectively score a page. And then finally, you may also want to, you know, do it in a very robust statistical way, which is to propose a null hypothesis test and assume that there is no difference between the scoring of pages or the topics. But this whole process can be kind of built, and can be, you know, just one example. We'll go to another later. And then finally, of the Venn diagrams, this will be the last one I will show, I promise. So this is actually showing how government, so DSTL, so this has been taken from DSTL, sort of like, I think it was from a short little book that they produced. I can't remember the name of it off the top of my head. So this is how kind of the modern day view of government data science is, which is that you have on the kind of right hand side what we would consider data science generally. So it touches on predictive analytics, database classification models, things that are kind of seen on the sort of more advanced side, I think it'd be fair to say for local government. So natural language processing is now more considered machine learning, as well as speech and vision. And then the artificial intelligence side we can broadly ignore, because you tend not to see those as frequently. So the example would be potentially something like deep learning. I think, even though it does feature in speech and vision, there are certain techniques that I guess would be more broadly considered artificial intelligence. This kind of very left-hand side, we can certainly ignore artificial intelligence in many ways, because they're talking more towards a general sense of it. So in relation to data management, descriptive analytics, visualization, I would say that most of us are probably familiar with sort of doing descriptive analytics. We are using more common tools, I think, these days around Tableau or Power BI for sort of representing that data to more people and getting it in front of people. Data management is certainly for Warwickshire is now its own sort of central team, and so when we say about that, that is for us looking after, say, a data lake and managing that data in the customer view as well. So for me, the data science is, whilst this is a broad view of how government view it, I would also encompass machine learning as well into more of the general view myself. But obviously this is just to show you how government view it. Okay. So when we talk about, so just to go back as well on the previous one, when we talk about AI as well, we tend to really mean machine learning. AI has a view of being, there's a general AI or weak AI. So when we talk about most tasks, we're talking about solving a very narrow task. So let's say, for instance, if you want to count critical signs on video, that is actually it's a very generalized ability to do, say, 100 signs, but actually, you know, it won't be able to drive the vehicle with the same ability. So it's not a general AI, it's a weak AI, or you can occasionally hear it referred to as a narrow AI as well. So weak AI is as this describes, it's definitely not the Terminator. It's a part of machine learning called deep learning, which is just very good at doing narrow tasks very well, things that we wouldn't consider being particularly useful in a sort of, you know, we couldn't leave it to drive the car, but we can leave it to sort of solve a particular task. So these are more views of weak or narrow AI that you would see in a day-to-day environment. So I've sort of mentioned about object detection and reading signage. Even driving a vehicle to an extent is just very much a narrow AI, really, in that it's learned how to drive, but again, it couldn't, say, pick up your kids as an example, or feed them, or cook them, or cook for them. You also see it in time series and gaming for any that do play games, but in time series, actually, it's quite common to see it in forecasting now. And then finally, probably the most common one that any individual will see these days is around speech, language, and predictive text. So if you think of, say, WhatsApp or Facebook or any phone, modern day phone, it will predict text, and they tend to be neural networks. So they tend to give you a best guess based on the previous words that they've seen. But they also tend to be highly complex, and they can also be obviously difficult to explain. That's why sometimes if you ever use speech predictive text, it's generally very good, but it will also occasionally throw words that you may not expect. Okay. So getting into sort of machine learning as a general view, which is actually that we tend to see it in a very simple way of you have a set of input data and you want to classify. This is a classification task, by the way, which would be you have input data, you have a function that resolves and solves so that you get your class 1 or class 2 and you get these predictions. This is obviously a very simple abstraction. What f of x is could be broadly any sort of technique. However, these tend to be usually split when we talk about machine learning, tend to be split into unsupervised and supervised tasks. But again, these days the area has grown quite significantly and can actually mean several things. So this touches on it in this example, which is actually I think as a local government, you will see unsupervised and supervised tasks more frequently. Semi-supervised is another type again, and reinforcement is also again another approach that you can look at. But in general, if you're starting with machine learning, it would be likely unsupervised and supervised tasks. So if we were thinking in terms of the typical, if unsupervised, supervised and semi-supervised, and finally reinforcement are considered the approaches, then the two main goals really are classification and regression. And when we say classification, we obviously mean a label, say A or B, and regression, we are guessing the sort of next number within the next likely number. So I will move on to an example of the sort of difference as well in a second. So this really is just to sort of show the difference between the potential approaches. So let's say, for instance, with an unsupervised task, it's a case of you may not know what clusters there are. So it's a case of it could potentially be applying a clustering method, and then for it to sort of tell you roughly how does that break down given a certain amount of clusters that you sort of assign, given a number, it will try and work out how that data should be split. One of the advantages of it is that obviously having a machine look at something, it obviously gives a different interpretation than a human looking at it. So for instance, if we were looking at words or documents, it might be a case of actually there's very general themes that run throughout, but they may be somewhat obvious for a general reader, but actually there may be subtle underlying differences that a human might not pick out. And then with supervised learning, actually we know what the outcome should be, and we really are just trying to kind of optimize so that the input data comes out with what we expect the expected outputs to be. So you can see this playing, the left-hand one you can see playing, and this is an example of two methods that you can use. So the left-hand one is an unsupervised method in action, and so it's optimizing for 3 clusters, and it's just trying to, the X, the big red X here, the big yellow X here, and the circle here, as these are moving around, it's trying to split the data optimally so that they are in well-defined groups. And so that's what k-means is, the approach with k-means is. So it's an unsupervised task. And the one on the right is more around describing that we want to, or whenever we see a point, we always want to say that it is either a blue square or a red triangle. So with the green dot, if we say that k is, if we say k is the nearest 3 neighbours, we would say that the green dot is a red triangle. However, if we said that k was 5, we would then have to say that the green dot was most likely to be a blue square, because when we looked at the neighbours, we can then say that actually, you know, it's more likely to be more likely to be a blue square based on the 5 nearest neighbours. So it's something to keep in mind that actually, whilst it's a supervised task, it still relies on you know, some level of intuition, and actually outputs can still be different if we were just comparing these two clustering tasks. So it is something to keep in mind when you're looking to apply it yourself. Okay, so in local government, I would broadly see that these are likely the 5 tasks that you are looking to do as part of, if you are looking to get into data science, this would be how they would fall, which is, you know, we've already discussed classification as a task, which is, you know, is it A or B? You know, based on the data that we've input so far, are we likely to see a type A or a type B? Recognition falls into the kind of weak AI arena. So if we were looking for, say, road signs or, you know, our objects, for instance. So if we were looking for road signs, that would be a recognition task of recognizing the signage as and when we pass it. For filtering, you know, there's just the example of you wanting to return the most likely ones that could be of interest to you. And actually, so if you were looking at, say, cases or outcomes of an individual, you may want to look at, say, that individual and all their other properties and say, who else within the data set is most similar to this individual based on a given set of criteria. Anomaly detection is, you know, looking for those outlier events, looking for something unusual within the data. And then finally, prediction is also something that we, which is also related to classification in a way, which is, but more broadly, we could say that, you know, let's say for financial forecast, based on how many particular, say, residents you may have in or look after, you may say, you know, how likely something may go up or down, or how likely they are to be at risk in the future based on particular criteria. So that would be where prediction can also be useful. Again, I will kind of touch later on the ethics side of things. So yeah, you have to be careful. Anything to do with predicting on humans is definitely going to require some considerable thought. Okay, so when it comes to the sort of approach to how you tackle, you know, a machine learning problem, usually this enters into several steps, which is if it's in this example, this would be a potential classification, let's say. So we may say that we want to look at, you know, train the model that we select, you then want to go through the process of actually validating it. So usually you have like what's typically considered a train test split. So the idea is to ensure that it's fit or isn't skewed in a way that isn't that is still useful and actually is going to sort of become generalizable in the end. So this also goes through a testing process as well, which you test potentially again on depending on your method or approach. You can either do a train test split, which is the only thing that you do, but people tend to have holdout sets as well, which is something that just isn't seen at all, rather than say a data set that you split into the training aspect and then the test. The training element is the part that gets fed into the model of choice. So if that's a sort of classification task, that might be a logistic regression as an example. And then finally, you tend to evaluate. So whether that's whichever's the kind of most valuable thing to evaluate on. So accuracy isn't always the best measure of a task. If we were thinking of something around people, actually it's probably better to occasionally be on the cautious side rather than saying that you are 99% accurate or 90% accurate. It's better to say actually we'll use a sensitivity metric instead to say actually you are likely to get some false positives, but that may be better in a particular instance. So it's better to see occasional ones where it gets it wrong, but it's just to be on a safe side. Okay, so Warwickshire is obviously a county council at the minute. There will be some of you that are county councils. There will be others that are district or borough or city councils as well. So the tasks that you will have will range from some of these to all of them to potentially none, I'm afraid. So I do apologise, but hopefully this is broadly reflects your type of work as an organisation, and this comes into what I would consider several different areas: assessing risk, customers segmentation, decision support tools. So in general, any tool that you build around people, and very likely is going to be the pressure point for most organizations here. Really, you're talking about a decision support tool. It's very unlikely that you're going to build a tool that will just make decisions on its own. What you're really looking to build is actually a tool that helps support maybe a clinical observation, for instance. So if you were saying that potentially a child is at risk because it's an area of interest or an area of importance as well, actually a model can help support a view of whether or not it's deemed based on previous data that child is likely to be at risk, but actually it's still down for clinical observation to decide ultimately whether or not that child is at risk. So it's really important to make sure that clinical observation is observed. And then I've kind of touched on many models, many tools as well. So if we were thinking of in terms of say food banks as an example, in certain areas and particularly within Warwickshire, actually the north and south look very different to one another. And it might not be that just because you build a model that works for the whole of your area, it might not necessarily be applicable to all areas. So actually you may need to build multiple models in very specific, tightly defined areas. And I think a good example would be, say, with if anyone looks at food banks, the example would be, say, that actually there are a lot of canned foods that go to food banks, but actually there may be cultural or religious reasons why a particular subpopulation or area that you serve just wouldn't accept canned food. So it's potentially, you may have a model that's incredibly accurate for 65% of all your service users, but actually certain subgroups or potentially subpopulations may just find that actually this tool just doesn't work for them. So you do have to be conscious of tightly defined remit as to how the tools are supposed to be used, and additionally as well, you have to be receptive to the fact that some tools may not be appropriate and have to be kind of considered as actually they need a different method altogether. Okay. So in general, we would say that actually it's not just say the model that you need to build. I think everyone, if you're doing data science, everyone would argue, it's cleaning data, doing the model, and trying to get a prediction. But actually, there's lots of other areas that you need to focus on as well, which is whether or not actually, you have the legal grounds to do the work in the first place. And actually, even if you do have the legal grounds to do it, there's the issues around the ethics of what you're considering doing. So actually, would most of the people that you serve, would they expect you to do some of these tasks? For some organisations, for some city councils, they've obviously explored these areas, but they've asked the public as well to just ensure that actually, are you okay with this? I think that's probably best practice to make sure that you ask your users before you go off and use their data in ways that they may not expect. In some cases, they may already sort of assume that you are doing the work, so it's something important to keep in mind. Again, probably shouldn't have to tell anyone here, but ensuring that you've got your DPIA set up as well is obviously necessary to do this type of work, and ensuring how that looks. The EIA is a equality impact assessment, so more as the fact that we're here to promote equality. It's also important that actually it's worth probably doing just an impact assessment in terms of just making sure that is this going to affect any groups that you may not immediately think that it would affect, or does it have the potential to affect them? And then finally, there's the cost and environmental impact as well that you may want to consider. So for instance, if we were thinking in terms of deep learning tasks, if you're looking for signs on the highway, the reality is that actually it takes a lot of resources to train a model from scratch. Deep learning models are CPU, GPU, depending on what you're using, TPU expensive as well. So actually the environmental impact should be considered if you're building deep learning models from scratch. It may be a case of actually transfer learning, which is sort of taking someone else's model and altering it slightly is probably the better preferred method. So if it's a case of being 97% accurate or 93% accurate, but you haven't spent 60 days on training it, actually the environmental impact might be considered important as well. And which leads me to, I didn't think that had I don't know if anyone else just saw that, but that seemed to slide in the title. I didn't think I had any animations on this, so apologies. So this is probably quite a large topic in and of itself. I know I sort of touched on the ethical considerations, but actually data ethics is becoming quite a large topic now. There's issues, and if we were thinking of speech, for instance, we may argue that having customers call up and use a speech kind of model, where we recognise what they're saying, is a massive benefit to many customers, but we also have to consider actually, is it affecting people in a differing way? Are we isolating people or excluding them? And I think when you're looking to, say, transcribe with a particular task internally, we're looking to, say, transcribe audio calls, for instance. And actually, it does seem to have, you know, if you look at the sort of confidence and inferred, you know, speech and transcription that is believed to have been said, actually, you know, really, it does differ between individuals. That could be based on age or whether or not there's a strong accent in the call. So actually, you do have to take into account, are people going to be excluded in the future? What is the impact of this overall? Does it worsen the service for others if their accent is difficult for the model to understand? So it does touch on the equality and impact assessment. So the equality impact assessment is a thing identified in law, but actually data ethics is a kind of, there's no hard, fast rules outside of the actual legislation itself. So this is probably the thing that you should aim to do as well on top of that. So aside from that as a topic, because that's quite a large topic, and probably there's certainly the Centre for Data Ethics and Innovation from government. Actually, there's several government bodies that now deal with data ethics. So certainly have a look at, you know, the Office of AI and others have their own, and the Alan Turing Institute as well. So they're all big kind of areas looking at data ethics, and more broadly other international, so other countries also publish work around data ethics, which is considered good. But finally, I think I'm going to stop with the kind of examples there and probably go more through a demo of, rather than, so just an example of where you may apply this. So if we had a task, for example, of so the task that we will discuss, sorry, is similarity. So this is a information retrieval task. You will see this as part of the data science area, if you like. The example we'll go through touches on, you know, one of the metrics that you may see or approaches you may see that kind of features quite heavily in lots of other approaches as well. So it's quite a foundational approach that we'll look at. So, and it just describes it as an example alone. But today is not going through the code, so that'll be the next session. But this will go through like the business problem that we might want to look at. So the example of the business problem is, so the council wishes to trial an intervention that they would like to deploy as part of a randomised clustered control trial. So when we say a randomised control trial, we would typically say that, you know, it's considered the sort of gold standard. The clustered part is solely that we're going to probably do this on a geographical level, so which is, as you know, as local government tends to be an approach that we would probably favour. So we're going to work through it as a hypothetical. So we've randomly selected the ward of interest and would like to know the most similar areas in terms of population growth and age of a child or age of children. The intervention is going to be against 0 to 2 year olds. And then we want to return the most similar wards given that randomly selected ward. And I should say as well, for the for the actual demo that we'll go through in the second session, it will be quasi-experimental. So we will select, for the sake of ease, we will actually select a named ward and then compare against it. But again, it's simple to try and change that to random for the future. So in terms of like how we would approach that business problem of trying to find, so how do we solve so that we always return the most similar wards given this ward? Well, actually, this problem can be thought of in terms of linear algebra. So if we considered the three figures that are related to each area of the population, so 0, 1, 2 years of age, that's one part of it. Or, sorry, 0 to 2 years of age, sorry. Then we can get an idea of growth rate based on population figures over, a given set of years. So let's say, 10 or 20 years, which is a linear regression that we could just use for that as an idea of a number. So just a simple line of best fit through the data. And then finally, we would need to write a function that can compare one area to all other areas and return the names of the three most similar areas, which will be what we will do in the second part. Okay, so the approach that we're going to use is called cosine similarity, but to give an example of mathematically how that would look and how humans would think about, say, an area, is actually if we considered the area of interest as being a list of ones. So we are looking for an area that essentially would match this row up here of ones. And so if we were thinking of it as humans would, we would say, well, another list of ones would also be a perfect match. And so we would say that one is considered perfect numerically. And cosine similarity in terms of the mathematical approach is also, they would agree, mathematically we can say that we agree with that as well, which is, yeah, that's a perfect match. Now, when we go into slightly fuzzier, imperfect combinations, when we look at comparator B as there's 2 1s and 2 0s, again, humans can tend to think of that as, yeah, that's about half right. And mathematically, it starts to look slightly differently now, which is, you now get 0.7, which is obviously not how we would think about it, because we can simply see that actually, half of it is right, half of it is wrong. We would see it as, it's about half. Again, if we were thinking of 3 1s, 1 0, we would say it's about, 3/4 correct. And again, in relation to any of these, it would look very similar. In fact, if it was all zeros, we would say it would look 0. And where we may take a slightly different view from the sort of the mathematical approach is to say, well, what happens if all the numbers were -1? I've taken a bit of a leap of faith and assumed that all other humans thinking about this would also think -1. Actually, they probably would think of it as a 0 or something entirely different. So that kind of gives an approach of a very simple idea of when it's just 1s and 0s, but actually, the numbers that we will deal with are never really like this. So if we were now thinking of areas of interest where the numbers aren't 1s anymore and the comparators aren't 0s or 1s, you suddenly realise actually scoring this as a human is quite difficult. We could have a guess, but 1450 is very close to 1500. 334 is very close to 349. 2940 to 1700 isn't that close together, and again 245 isn't really, but based on some of these other figures, you would say, we may say that actually these others are, we kind of get the intuition of the similarity approach, so we can say, yeah, that is pretty close to those numbers. That's further away. Comparator C looks very similar in multiple categories actually. So you can kind of understand that actually how the mathematical approach is working out. There is some human intuition, that if we were really looking at the numbers, it would start to make a bit more sense. So I have just clicked on this. So this is the actual approach that we are going to use. So it's called cosine similarity. We will build this in the part 2. Now, I don't necessarily want anyone to be put off by the maths down on the right hand side, because in reality, all we're really doing is we're saying take list A and take list B, and then just for each of them we're going to times them together, and then beneath that we're then going to times them together. So we're going to add the list together and then just do square root over their squares. For absolute completion, the sort of explanatory notes, I would say, should say that similarity is equal to cosine theta, which is equal to A dot B of the L2 normalization, the absolute values or Euclidean distance, which is equal to the sum ith term in A multiplied by the ith term in B divided by the square root of the sum of each squared element of A-ith term times the square of the sum ith squared element of the B-ith term. So that doesn't seem all that intuitive if you're not from a maths background. I think this probably makes more sense as a sort of demonstration, the left-hand side. So hopefully that makes sense, and you get this number between you tend to get the number between 0 and 1, which is represented as an angle, which is considered so the angle is considered theta. We usually express it as on a right angled triangle. Excuse me, as a right angle, if we think of a right angle, but it can be expressed negatively as well. But all we're really doing is that A and B, and this is a very simple demonstration, which is that we're saying that A and B, theta is just the distance in sort of the difference between the two. If you think of it in 2 dimensions like this, I think this probably makes more sense. Obviously we can't demonstrate 4-dimensional space, so hopefully this does make sense, that all we're really doing is an angle or a distance, if you like. Okay, so that's the kind of the intuition for part 1, and just to sort of touch on the fact that why would we do similarity or cosine similarity? Well, you can use it so broadly that it's kind of rooted in lots of other sort of approaches as well. So these are some examples of where you may see the approach exist. So comparing people, normalizing documents, or obviously most tasks that require information retrieval. These are all areas that you might see them, the use of cosine similarity. If you're looking at, say, hierarchy, of text documents, you can also use cosine similarity to measure distance as well. So it's got quite a broad application. You will see it featured in lots of different algorithms as well if you choose to have a look at it. So it kind of presents kind of a very intuitive technique, but also as well kind of it's a good piece of maths to understand. Okay, I mean, that is sort of the end of part one. I open it up to questions, if that's okay. I'm going to stop sharing my screen if that's all right. So is that okay with everyone? Hopefully that was clear. So that what we'll do in part two is then actually go through the Python, go through a Python script that I will annotate and run through so that we can I can explain it as we go. So that's how I would see it going. Hopefully no one was expecting any Python today, because that will be what part two will be for. Is there any questions or any sort of general points anyone would like to make? Hopefully I've not sent everyone to sleep. Hi, Christina.
Hi, I don't really have a question. I just wanted to say thank you very much, because I've seen like lots of bits of this before, but you've put it in a really, really clear way for everybody, like whatever level people are at. Like,
okay.
And I'm not a doer. It's just a hero. But yeah, it's really clearly explained. So thank you.
Okay, well, that's good to hear. Sometimes it's a bit worrying talking into the void.
Yeah, you don't have any response. You want to see people nodding along, or
ideally, this is why I would like a room. Thank you, though.
Thank you. Thanks.
Just to answer that question that I've just seen about sorry, hold on. There's so what Python interface do you recommend? So I tend to use Jupyter Lab. Jupyter Notebook's absolutely fine. It's likely Jupyter. I also use Visual Studio Code, so that has built-in notebooks now. It is really entirely up to you, Carol. It's whatever you're comfortable with doing. If you use a kind of like Jupyter Lab, if you looked at more advanced things, they tend to play better with, say, topic modeling, visualizations and things like that. So that's what I would say. In terms of the, I think I've just seen a question about the slides. Yeah, I can make the slides available to the LGA as well. Okay, excellent. Actually, Kate's already responded. Is there any further questions? So we will go through the sort of Python at the minute. Also, just to say, which I don't think I. I'm not sharing my screen. Okay, there's a placeholder at the moment for the code, which I'm just gonna copy and paste for now, which is where you will find the code when I've uploaded it. So if people want to pull it, that will be available from the 1st of December. So just so that you have the link available to you. At the minute though, it's just placeholder. So I will write some explanatory notes for it.